Okay, in part B of the structure of the atom, we're going to look at the continuous spectrum, we're going to look at absorption spectrum, and we're also going to look at the concept of fluorescence. So up until this point, we've been talking about the spectrum of gases, and in particular low density gases like, for example, hydrogen. But what we want to talk about now is what happens if we have a solid, as in a filament in a wire, a liquid, or a dense gaseous object. And what happens there is when the atoms are excited in those is that they release all of the colours. So we have lots and lots of charged particles within the solids or dense gases or liquids, and they're all oscillating really, really fast as the particles move really fast as it gets hot, and they produce a whole range of electromagnetic waves as they all oscillate, because a vibrating charge causes an electromagnetic wave, and we see the whole spectrum of light if we look at that. So if we look at the sun through our spectroscope, or if we look at an incandescent light bulb, one with a filament in it, we'll see this continuous spectrum containing all of the colours. Now the distribution of the spectrum really depends on the temperature of the filament or the temperature of the dense gas in this, if you're dealing with a dense gas. So at lower temperatures here, T1 is our low temperature, we'll see basically it'll be towards the infrared part of the spectrum, so less energy, less frequency. We could have frequency or energy here because they're proportional. And often when we start to heat things up, we'll say that they go red hot. So red hot though is about there. Then as we get hotter and hotter, we'll see it will start to radiate right through the visible region. So if we've got something like this with all of the visible colours, that will appear as white light. And then if it gets even hotter, eventually we actually start to get this skewed towards the ultraviolet end of the spectrum, so things will almost appear, if you like, blue. We'll often talk about something being blue hot. Blue hot is, if you like, in the scale of colours, there's red hot, and then if you get hotter, you get white hot, where you have all of the visible colours emitting, and then eventually you get blue hot, where you've pushed this distribution towards the blue end of the spectrum, towards the UV end. So we see this if we do use a filament in an incandescent globe with just a low voltage, it will appear quite orange or red in colour because we haven't got that high temperature, so we get more of these colours. When we turn up the voltage, we'll tend to see white light because we'll have all of these vibrations occurring. If we think about burning a Bunsen burner, we tend to see the reds and oranges when the air hole is closed at the lower temperatures. As we open the air hole, we tend to see a blue type flame because the particles are hotter and they're emitting light more at this end of the spectrum. Okay, so now we're going to look at line absorption spectrum. Basically what a line absorption spectrum is where we take a continuous spectrum, so all of the light, and we shine that through a cold gas, not a hot gas now that's being forced to emit light. And we look at that through a spectrometer, and we see something that looks like this, where there's the continuous spectrum, but there's a few little lines missing. So why are these lines missing? Well, when light with a continuous spectrum is incident on the gas of an element, discrete frequencies of light are absorbed, resulting in a line absorption spectrum. The frequencies of the absorption lines are a subset of those of the emission spectrum of the same element. That doesn't make much sense. Think of it a bit like this. If we've got our element here and it has these energy level gaps in it, and we shine white light that has a whole range of colours, if the light corresponds to an energy gap here, so it has to correspond to an energy level gap, then it will be absorbed by this atom and the atom will go into an excited state. So in this case, the blue and the red have been absorbed because they correspond to those energy level gaps, but the green and the yellow have kept going through. So those ones that are absorbed appear as these black lines here. So light, a good analogy here is a ladder. So light can only be absorbed if it corresponds to exactly to an energy level gap. The same as if you climb a ladder, you can only either be on one rung or the next rung. You can't stand halfway in between a rung. Well, light that's halfway between a rung or halfway between an energy level can't be absorbed. It can only be absorbed if it corresponds to an energy level gap. So that is, if you like, what produces the absorption spectrum. Just for completeness, this is not really that difficult, but it is in the course. If we want to know, obviously we've got the hydrogen spectrum, so draw on an energy level diagram transitions corresponding to the line absorption spectrum of hydrogen. Well, that is these ones here. So the arrow goes up for absorption because the atom is absorbing it and pushing it into a higher excited state. Just continuing here, explain why there are no absorption lines in the visible region for hydrogen at room temperature. Well, basically hydrogen, if it's at room temperature, is all normally down here in the ground state. There's not enough kinetic energy of the particles at room temperature to put it into this first excited state here, the n=2 state. So that means that we'll only see absorption lines here if the hydrogen is already in a fairly energetic state, because the ones that would correspond to the absorptions that would be in the visible region would be these ones here. So these are all absorption lines, same as the subset of the emission spectrum. So we won't see those because there's not basically 10 electron volts of energy at room temperature to push the atom up into that state. And so that's basically what that says there. So account for the presence of absorption lines, also known as Fraunhofer lines, in the sun spectrum. So if we look at the sun through a very good spectroscope, we'll see this sort of pattern in the sunlight. And that is because there's hydrogen and helium atoms in the sun's atmosphere, and they absorb light of frequencies corresponding to the energy level gap. So obviously we have hydrogen here, but helium would also absorb some as well. So when you look carefully at the sun, you can see some of the bits missing, which gives you information on what is in the atmosphere of the sun. And this can be used to also look at distant stars and analyse the composition of distant stars and other things in outer space. And finally, for this video, let's look at the concept of fluorescence. I think this is pretty straightforward. It's not one of the concepts usually people have much trouble with. When an atom absorbs high energy photons, it is elevated to excited state, energy states above the ground state. Excited states are generally short-lived and the atom quickly returns to its ground state, often by emitting a series of lower energy photons. This process of converting high energy photons into a large number of low energy photons is called fluorescence. So in essence, if we take the hydrogen spectrum here, because I've got a copy of that and it's an easy one to use, then if we excite, say, the hydrogen atom into that state, it can then decay by a series of steps. I could have drawn these all different colours, I guess, but I was too lazy for that. So this is the idea: excite the atom into a high state, then it decays by a series of smaller steps. Usually this happens quite quickly. Sometimes it can happen over a longer period of time, and that's where you get the idea of like things that are luminescent. So when you turn the light off, they still glow in the dark because there's basically atoms in an excited state and they are slowly relaxing over time and releasing that light. That idea of a long-lasting excited state, which is what causes the sort of luminescence behaviour, is going to become very important in the next video when we talk about how lasers work.